Okay, physicists, today is our pre-test review. On Friday of this week, you're going to see a test of a familiar form. This is the Unit 2 formula sheet as it now stands. You should expect to see 10 multiple choice questions, 5 true, false, and 4 multi-part short answers. I'm going to talk about what specific things you're going to see more as we go on today. But so far, you hopefully have been looking back at your homework assignments to check the solutions, make sure that you understand how to do those. And today, a 20-question review packet has been posted on Canvas. So I recommend that you try to do that and make sure that you understand every question in that by this Friday's test time. Okay, so a surprising amount of this test, since we've just gotten off of energy and work, you might not be thinking about forces, but almost all of this test is about forces because we haven't tested over it yet. So the three things to remember, of course, as our core are Newton's first, second, third law. First law says motion and not motion are both natural. If you're moving, you tend to keep moving. If you're not moving, you tend to keep still. What you need to explain then is with Newton's second law. If you accelerate, so if you start moving faster or slower, or if you start moving at all, if you're not moving, then you have to introduce the idea that there's a net force acting on that object. And the amount that an object accelerates depends on its mass and how much net force is applied. The third law says, for each one of these forces that you're applying, there's another force. If I push on my hands together, this hand pushes on, my left hand pushes on my right hand pushes on my left hand. They're going to push each other with the same force. Equal magnitude, opposite direction. So let's see how these play out in a couple of different problems. So for instance, here's a nice first law practice question. It says, the block shown moves with a constant velocity on a horizontal surface. Two of the forces on it are shown. In addition to this, there's a frictional force exerted by the surface, and that's the only other horizontal force on the block. The other frictional force is what? Well, the key here is constant velocity. If you have a constant velocity, your acceleration is 0. Now, what does that mean? That means that the F net, the total force, is also 0. Okay? So if I have 5 newtons pulling this way, 3 newtons pulling that way, if I'm going to have the total force as 0, I've got to put another 2 newtons right there. So 2 newtons leftward, done. Okay, so the key thing to remember is that constant velocity does not mean there's a constant force. It means there's 0 net force. And if you have any applied forces at all, you have to apply forces in the other direction that will cancel them out. Okay, here's another one. Equal forces act on isolated bodies A and B. The mass of B, mB, equals 3 times the mass of A. The magnitude of the acceleration of A is it 3 times that of B, 1/3, the same, 9 times 1/9? Okay, well, F equals ma. That's our Newton's second law. That's the one equation. If you're going to remember just one from this unit, that would be it. Now we're given that the F m b a b is going to be the same as F of mass A times acceleration of A. However, we're told that the mass of B has 3 times that of A. So if this is 3 times B, then we would expect let me put it this way. Here's your 3 times MA is MB. So then we find out that the acceleration of B is going to be F divided by 3MA. On the other hand, over here, we have the acceleration of A is just F over MA. So it looks to me like the acceleration of A is about 3 times as big as that of B. Okay, this should not surprise us because smaller masses are easier to accelerate, heavier masses are more difficult to accelerate, which is also known as the idea of inertia. Okay, here's a trickier second law problem. Remember, F equals ma, it really is F net equals ma. And in a problem like this one, you have an 1,100 kilogram elevator, and it's rising, and its speed is increasing. So that means that you do have an acceleration, so the forces are not balanced. The tension in the elevator cable is going to be pulling up more than the force of gravity down on it. So we've got 2 forces in this problem. You've got the force of gravity pulling down and the tension force pulling up. And since the acceleration is upward, we know that the net force also has to be upward. Okay, so what you would do in this sort of problem is set up the MA equals, sorry, I'm not going to skip any steps. We would say that F net equals the tension minus the force of gravity. Okay, so that's the net force. Now F net equals ma, so I'm going to use Newton's second law. And the force of gravity, we know it's the mass times the gravitational field strength, so m times g. Okay, so if I want to find out what the tension in the elevator cable is, I would just go ma plus mg. That's my tension, and in this case the mass is 1,100. G is around 10, and so 10 plus 3 is around 13 newtons. So 1,100. So it's got to be that one. So the sort of tricky thing to realize here is that I did a lot of work in this example for nothing. If you realize that the force of gravity, this is an 1,100 kilogram elevator, is 11,000 newtons. So this is right around 11,000 newtons. And you know that the tension force has to be bigger than the gravitational force because you're accelerating upward. You have a net force. You could have picked this one and walked away. All right, so there are some advantages to having multiple choice questions. Okay, so Newton's third law says that every action has an equal and opposite reaction force. Now, a conundrum that we ran into here is, what if you have a horse connected to a cart or a wagon? The horse is pulling on the wagon is pulling back on the horse. The sizes of those forces are equal. How is it that they don't all of these forces don't just cancel out? Is it because the action force is greater than the reaction force? No. Newton's third law says they're equal. They act on different bodies. Yes, that's it. What happens is that the horse and the wagon indeed do have opposite forces, but you also have the ground and the horse. And so you're able to push off of the ground. The horse is able to push off the ground. The ground has a net force backward, but it has a really big mass, so we don't notice it. They're in the same direction. No, they're opposite directions. The reaction force exists only after the action force is removed. The reaction force is greater than the action force. They're equal size, opposite directions. Okay, so that's Newton's third law. Here's a little bit of a trickier third law problem because it has a tiny bit of flarf in it. Remember, my idea of flarf is that there's a lot of information that you're given that is not useful, that is out there to confuse you. And my assertion is that most of contemporary life is filled with flarf. Okay, and in fact, this question has flarf in it too. A 5 kilogram concrete block is lowered with a downward acceleration of 2.8 meters per second by means of a rope. Okay, meters per second squared. So if it's accelerating downwards, that means that the force of gravity is bigger than the tension force pulling up. Let's then read the question. The force of the block on the earth is. Okay, so this question is asking us to think about what are our paired forces in Newton's third law. In this case, I have a pull up from this tension rope. Presumably there's someone holding that or something like this, and there would be the tension pulling down. Force of gravity is pulling down on this block, but the block's pulling back up on the earth. Now it's a 5 kilogram block, so this is going to be 5 kilograms times 9.8 newtons per kilogram. So that force is right around 49 newtons. Hence, the force pulling up is 49 newtons as well. That's the answer. So this extra piece of information, which looked so useful, looked like we were going to have to use it in the problem, that was flarf. You don't need it. The forces are in Newton's third law are always opposite directions, equal sizes. Now, as I've showed you before, I'm crazy about Atwood machines. I like these types of problems. I think they capture most of what we're interested in about this unit. It tells me that I have a 70 Newton block, so this is around 7 kilograms. I'm just dividing by G. And a 35 Newton block, so this is right around 3.5 kilograms. Being a little sloppy, but it'll be good enough. Are connected by a string as shown. If the pulley is massless and the surface is frictionless, the magnitude of the acceleration of the 35 Newton block is. Okay, now I would honestly probably give you this as a short answer question. The first part of your short answer question would be draw the forces, or draw the free body diagrams. So in this one you have a normal force pulling up, you've got a gravitational force going down, and you have a tension force going over like this. That's for my 7 kilogram block. And then for the other one, you have the tension force pulling up, and you have the force of gravity going down. Okay, these are not the force of gravity. Let's call that FG1, FG2, or something like that. Different forces of gravity for the different objects. The tension force is the same though, and what else is the same is the acceleration of these two blocks. So for each of these now, I'm going to write a F equals ma equation in the direction that they're going. So for the first object, I'm going to write 7 kilograms times A equals the tension. For the second block, I'm going to write 3.5, so this is F net equals m times a. We're going to do the same thing for the other one. F net equals ma. Now the F is going to be t. And then the other thing is that in the direction of its motion, we have to include that 35 newtons. Okay, now it's asked, and the other tricky thing here to realize is that this is, the 35 newtons is what's doing that acceleration, so this is going to accelerate it downward. So I'm going to put a minus sign in there. Okay, now I want you to find out what the acceleration is, and to do that, I'm going to take this, I'm going to put it in for t. So minus 3.5a equals 7a minus 35, and then I can bring this over. Minus 10.5a equals minus 35, and you get your a is right around 3.3 meters per second squared. Easy peasy. Okay, now on your test, what I'm expecting to give you is a problem that's more like this, where you have a mass here and a mass there. And they have this one has a tension pulling up, this one has the tension pulling up. They both have gravity pulling down, and I would ask you to figure out what the acceleration of the block is. Okay, so obviously the bigger mass is going to accelerate it, so you can set up the equation. So think about that, and you'll see an explicit problem with that on Friday. All right, now in Unit 2 we did lots of different forces. We talked about gravitational force, the normal force, which is the push of a surface back up on the object that's resting on it, perpendicular to the surface. Frictional force, taken to be parallel to the direction of the surface. Tension forces from ropes. Gravitational forces. We also talked about spring forces, having to do with the stored energy of the K, which is called the spring constant. And then we also talked about problems involving things going around in circles at constant speeds. And in that case, you can figure out what the net force is, which is called the centripetal force, because that net force is always changing direction, always directed towards the center of the circle. All right, here's a good conceptual problem. It says, a crate rests on a horizontal surface and a woman pulls it with a 10 Newton force. Rank the situation shown below according to the magnitude of the normal force exerted by the surface on the crate, least to greatest. Okay, now, the thing to realize in this sort of a problem is that even though there's a force sometimes being applied horizontally, that means that the block could be sliding horizontally. In this type of problem, if there is a normal force, it means that the object is resting on the surface. If it's resting on the surface, it's not accelerating up and down, so the total force in the y direction is 0. So for instance, in this first case, I have my gravitational force and my normal force, and there's my 10 newtons. Now that 10 newtons is acting horizontally, so it's not going to contribute one way or the other to the normal force. In this case, Fn equals Fg. They're going to have the same magnitude. They're opposite directions, but same magnitude. On the other hand, right here, my gravitational force is pulling down. This 10 Newton force is pulling somewhat up. So in this case, my normal force is also pulling up. And so I would have my Fn plus F, the part of that force that's pulling in the y direction, plus F sine theta equals Fg. So these are the ones pulling up, that one's the one pulling down. In this third case, Fn is going to be even smaller because F is pulling all the way up in the same direction as Fn, and Fg is now down. So in this case, Fn, so 1, 2, 3, Fn plus F equals Fg. So if we want to rank the magnitude of the normal force, this is the biggest, this one's the smallest. Okay, so it would be, if we were ranking them least to greatest, it would be 1, 2, 3. Easy. Okay, of course, a good question to think about is, what happens if this force were pushing down and that one were pushing down instead? Then it would be 3 to 1. I'll let you think about that. Okay, now, this is a tricky problem, and I am going to give you one that is almost exactly like it on the test. So let's read it carefully. We have a 40 Newton crate, resting on a rough horizontal floor. 40 newtons means that the force of gravity is 40 newtons. A 12 Newton horizontal force is then applied to it. If the coefficients of friction are this and that, the magnitude of the frictional force on the crate is. Okay, let's think our way through it. Force of gravity is pulling down with 40 newtons. Now that force that's being applied is perpendicular to the force of gravity, and so it does not influence our normal force. In this case, our normal force would just be 40 newtons. Now, if I have an applied force pulling forward, my force of friction is going to go backwards. And in our friction models, we said that the force of friction is going to be different depending on whether or not the object is moving. If the object is staying still, so there's going to be some static friction, would be the coefficient of static friction, 0.5, times the normal force, 40 newtons. On the other hand, if my object is sliding, you have a frictional force that's done with kinetic friction, 0.4 times 40 newtons. So there's your static, not moving. This is your kinetic, moving. So that is 20 newtons. And this one is 16 newtons. Now, the first question we have to ask is this force sufficient to get my object to move? Well, how much force would I have to apply to get my object to start moving? I would have to apply 20 newtons of force. After that, once it starts moving, I only need to apply 16 newtons. In this case, we have only applied 12 newtons of force, so my object is not going to move. Notice that this is a maximum amount. It's not just a number that you can just use without applying a little bit of thought. So, if my object is just sitting there and it's not accelerating because I haven't applied enough force to get it unstuck, that means that the total force in the x direction is going to have to be 0. Hence, if this is 12 newtons, the force of friction also has to be 12 newtons. Okay, so that's a little bit of a tricky one. I encourage you, if you encounter a problem like this on the test, to write out as much as you possibly can, draw a free body diagram, do some calculations, and you can get a lot of credit even if you're somewhat stumped. For instance, in this problem, we've got this 12 newtons, but let's say that we had applied 22 newtons or something like that. In that case, we would know that our object had started moving, and then we would be using our kinetic. In that case, we'd have 16 newtons as our force. So there's a lot of physics in this problem. Now here's another one that's sort of like the first one I showed you. In this problem, a boy pulls a wooden box along a rough horizontal floor at a constant speed. So that's the important thing. At a constant speed means what? It means no acceleration. No acceleration means what? It means that the net force in every direction is 0. So in this case, it's asking me questions about the force of friction, N, the magnitude of the normal force, Fg, the magnitude of the force of gravity. Now, okay, it wants you to compare P and F and N and Fg. Well, P in this problem is up at an angle, so it's going to have part of its pull along the x direction and part of its pull along the y direction. Now, if these forces are balanced, it means that the x component of P has to equal F. But if just the x component of P equals F, that means that P has to be greater than that frictional force. Why? Because only part of it is already equal to it, so the whole thing has to be bigger. Okay, now let's think about the y direction. How are the normal force and the force of gravity going to compare? Well, this P is pulling upward, so that means that the normal force plus P is going to cancel out the force of gravity. Hence, the force of gravity has to be bigger than the normal force. Okay, so normal force is less than force of gravity, yes. P is greater than F, yes. There we go. Again, if you're stuck on this type of problem on an exam, draw out the picture, list what you know, give me whatever reasoning you can. Okay, same thing with this one. This one is going about our centripetal force, where we have our objects that are moving in a circle. You have some mass. You have the acceleration is always towards the center of the circle. The v is always the instantaneous speed is always tangent to the circle. In this problem, it says if you have an object moving in a circle, if the mass is tripled, so mass goes to 3 times mass, and the speed is half, so v goes to 1/2 v, and the radius is unchanged, so r just goes to r, then the magnitude of the centripetal force must be multiplied by a factor of what? Well, the centripetal force is mass times acceleration. A in this case is that v squared over r. So if our original F was mv squared over r, now we're going to have 3m 1/2 v squared over, and r didn't change. So that's going to give me 3 times 3m times 1/2 v times 1/2 v, that's what squared means, over r. And so my F equals 3 over 2 times 2 is 4 mv squared over r. Okay, so I've got a 3/4 out front. I like that type of problem. I will almost certainly give you something that's pretty similar to that. Okay, last force one. Remember when we did also a number of problems involving the inclined plane. In this case, it says you've got a 32 Newton force parallel to the incline is required to push a certain crate at a constant velocity up a frictionless incline. Okay, constant velocity means what? It means 0 net force. That is 30 degrees above the horizontal. The mass of the crate is, okay, so you're pushing this up with a 32 Newton force. Now remember, what we did in this type of problem is we split the force of gravity into a y component and an x component. And so the y component doesn't matter here because that's going to just be canceled out by the normal force. What matters is going to be that mg sine theta force pulling backwards. We're given that angle is 30 degrees. This angle is the same as that angle. And so what you have here is that 32 newtons equals mg sine theta. What are they asking for? They're asking for the mass of the crate. So m is going to be 32 newtons divided by g sine theta. And you know your triangles. If you have a 30, 60, 90 right triangle, this is 30 degrees. There's 1, 2. So sine of 30 is 1/2. So this is m is going to be 32 newtons. G is around 10 times 1/2. And so think of that as about 64 divided by 10. It's got to be this one. Okay, so we've done a lot of these force problems. That's going to be most of the test. However, there are also going to be a few questions on our work and energy stuff. Remember, the idea that we have is that if an object is moving, it has kinetic energy. Kinetic energy is 1/2 mv squared. If you want to get the object to move faster, you're going to have to put in work. If you want it to go slower, you put in negative work. And the picture that we have is that the amount of work done on an object gives you how much its kinetic energy changes. The other idea that we had in this unit was the idea of energy conservation, where you add up the total amount of kinetic energy plus the total amount of potential energy and set that as, and say, if we're not putting work in or out of a closed system, the objects are just going to trade their energies around, and we can use that to solve some problems in a sort of a slick way. Okay, so here's one that's just asking you to use your work energy theorem. You have a 5 kilogram cart, so m equals 5 kilograms. You have an initial speed. V initial is 6 meters per second. You have a final speed of 10 meters per second. And it says the net work done on the cart must be. Well, our kinetic energy, our work energy theorem says that whatever our kinetic energy is at the end, our final kinetic energy, is whatever our kinetic energy was at the beginning, our initial kinetic energy, plus the work. So in this case, all I would have to do, 1/2 mv final squared, I know those numbers, equals 1/2 mv initial squared. Use those numbers plus the amount of work done. And the amount of work is going to be positive because we caused that cart to get faster. Okay, I'll let you solve that one on your own time. Okay, similarly, so that was a positive amount of work that was put in, and it made our object get faster. Now, if I have an object that's just going at the same speed, that means that my total amount of work that I'm putting into the system has to be 0. However, that doesn't mean that there's no work being done at all. It means the net work being done is 0. So here's a case, for instance, where we have a load and it has a weight of 5,000 newtons. Okay, so that's the force of gravity on it. It is pulled on level snow by a dog team exerting a horizontal force on it. We're not given the size of that force, but we are given the coefficient of kinetic friction, which is going to be 0.05. How much work is done by the dog team pulling the sledge 1,000 meters at a constant speed? Okay, well, notice here we know the force of gravity, so we know the normal force. It's just going to cancel out our force of gravity. And because it's going at a constant speed, we know that the force of friction is also going to just be canceled out by this force forward. Constant speed means no net force. So force of friction is going to be the same size as that force pulling forward. The net work here is going to be 0 because it's not speeding up or slowing down. However, we know that you actually have to put in work to counteract those frictional heat losses that you get here. But okay, so how big is this force? Well, the force of friction is going to be mu k times the normal force, so it's going to be 0.05 times 5,000. Okay, and we know that force is the work is going to be the force times the displacement times the cosine of the angle between them. The displacement is in this direction, the same direction as the dogs are pulling the sled, so my angle there is 0, cosine of 0 is just 1, so my work is just going to be my force times the displacement is going to be 0.05 times 5,000 newtons. That's the force, and then the displacement that they ask me to look at is 1,000 meters, and so it's just going to be, this is going to be 5 times 5 times 10 to the minus 2, 10 to the 3, 10 to the 3, so this is going to be 25 times 10 to the 6th, 10 to the 4th, which is 2.5 times 10 to the 5th joules. Okay, so there's my answer for this one. Dogs are doing positive work, friction is doing negative work, the net work is 0. Okay, now the last thing that I want to go over in this video is the idea of energy conservation. And this one I think I'm going to give you as one of your short answer questions. The idea of energy conservation is that if you add up at any point along this, if you have a conservative system where total energy is not coming into the system or leaving the system, you can add up all of the kinetic energy plus all the potential energy at any one point in the story, and it will equal the kinetic energy plus the potential energy at any other point in the story. So for instance, in this case, we have a simple pendulum consists of a 2 kilogram mass attached to a string. It is released from rest at x as shown. So its height is this. Because it's lifted to some height, it has gravitational potential energy. They're asking, what is its speed at its lowest point? Now, the traditional way to do this type of problem, or I should say the quick and dirty way, is to just say, well, at the beginning it has gravitational energy, at the end it has kinetic energy, and I'm just going to go mg times 1.85 equals, so that's my mgh, equals 1/2 mv squared. The mass, turns out, is flarf, and you could go ahead then and find that v equals the square root of 2 times 1.85 times g. Okay, so that's okay, that's fine. But what I want to encourage you to think about is that what energy conservation really means is that you have your gravitational energy plus your kinetic energy at the beginning, and you have your gravitational energy, so let's call that at 1, and you have your gravitational energy and your kinetic energy at time 2. In this case, the kinetic energy happened to be 0 at the beginning. The gravitational energy happened to be 0 at the end, and so we could do that. But in the problem I'm going to give you, I'm going to go ahead and ask at some intermediate place. So if you started out, you can start out with all gravitational potential energy. You don't let the ball drop all the way. You just let it drop halfway or something like that. You could still use this because you would just say mg, h top plus 0 is still going to be mg h at that time 2 plus 1/2 mv squared at that time 2. Okay, so you can use this type of energy conservation problem to solve for the position and the speed, or rather, you can use it to solve for the speed of the ball at any one of these heights. Okay, so that's the take-home message. Okay, so we've gone over a lot in this video. What should you expect on Friday? You should expect 10 multiple choice questions that are pretty similar to the ones that we've gone over today. 5 conceptual true-false questions about Newton's laws, about work, things like that. 4 short answer questions, and our 4 short answer questions are one is going to be a question where you have forces and you have to add them together as vectors, and then use your F equals ma, where F is a vector and A is a vector. So that's one. You're going to have your problem with tension and pulleys. I told you about that one already, where you have 2 blocks and a pulley, and the tension pulling up on this one is going to be the same as the tension pulling down on that one. Or sorry, tension pulling up on this one is the same as the tension pulling up on that one, but they're both going to accelerate. On the third one is going to be a problem where the frictional force is acting as the centripetal force for a car driving around a track. And then the fourth problem is going to be one with energy conservation, like the last problem that I showed you with a pendulum. Okay, so good luck studying. If you have any questions, I will be around for office hours, and please feel free to shoot me an email. So make sure that you've really looked at the review packet, old homeworks, and if you have any questions, please just shoot me a message. And good luck.